now you guys are ready for the hard stuff.
No.
Cellular respiration. The stuff we did for the first two exams, we're going to utilize over here. I'm going to do a lot of what I call art therapy up here. Okay? In these different colors. Everything is in your PowerPoints. My drawing's up there. I'm videotaping this, so it'll be up there too. My suggestion is, as I draw this thing, you could do it this way or not. This is my suggestion. I think it's best that you just sit back and enjoy the movie kind of thing. Absorb everything. You have it all on video. You want to draw them from my video. You could do that too. I think I encourage that. There's a lot of ways you're going to need to know how to go from this step to that step. But I think as I draw this thing, it's going to make things a little bit easier for you to do, as opposed to if you're drawing it with me, you're going to be losing out on certain things. So, but this stuff's important. This is ATP. All right. Let's get started with this. So let's give you a little introduction. Why this? The big picture here, the forest. Okay, and then we'll talk about the trees. So an overview is, here's the analogy that I came up with. Okay, why are we making a big stinker about this? It's like exchanging money, all right, when you go to different countries, all right? If you go to different countries and you have a U.S. dollar bill and you're going to Japan, that U.S. dollar bill is not going to do anything, but it's worth something, right? If you go to England and you have a U.S. dollar bill, you can't just go into a store and buy something. They use pounds. But you're not going to throw out that dollar, right? I mean, it's worth something. You know, even if you move there permanently and you bring 1,000 U.S. dollars, you're not going to throw that out. It's worth something. So we have to convert things, okay? So there's different forms of energy that need to be converted to something that's universal, ATP, okay? So all that money, the pounds, the yen, the dollars, the lira, all that money, if we convert that to gold, gold has a certain value universally. And you could change that to whatever you want in any country. Does that make sense? So we got to use, change everything to ATP. But things are worth things. And that's what I was showing you about with NAD plus or NADH. FADH2, you can't use that as energy, but we can convert it into ATP that we can use as energy. And that's what the big picture is over here, okay? That our bodies are just not making ATP, they're making things that hold a lot more ATP, but we can't use it. I can't go into a store and buy something with gold, I have to convert it, but everybody knows what gold is, okay? So, when you look at the big picture of the whole Earth, the way it starts off is that we have energy from the sun coming in, going to the plants. The plants can't go and eat a burger, so they have to make their own burgers inside of them. Okay? They have to make their own glucose. They're not getting it from eating sugar someplace. So there's a process here in plants, it's called photosynthesis, that takes the light energy, that takes our carbon dioxide. Why our carbon dioxide? Carbon from CO2 is going to be, when you put 3 of those together, you have 6, you could make glucose. And that's what it does, okay? So plants do a process of photosynthesis to make food. Now they got glucose. That glucose can now be put into their own mitochondria to make energy, okay? We can eat the plants, which is stored energy, and we could use that glucose from the plants to make our energy. So we eat things, okay? So whether plants, which is the bottom of the food chain, is going to make its energy this way, we start off over here. Either way, the mitochondria in the plants or mitochondria in animals are going to make ATP. The mitochondria is the powerhouse of the cell to make ATP. Whether we eat a burger in animals or just make their own food through photosynthesis in plants. Does that make sense? Okay? And then we make the ATP and heat gets put out. The key processes that we're going to be dealing with here are terms that we're going to see. Fermentation. I don't think we'll talk about that today. We'll get that on Monday. But fermentation is when we degrade or decompose sugars without the uses of oxygen. It's not the best way. Indeed, it is not the best way, but we can do that. Other animals or protists or other smaller animals can do that, and that's their form of energy. They don't need oxygen. We also have aerobic respiration, and that's what we mainly do. It's converting organic molecules and oxygen to make ATP. So we need oxygen. When we do, it's called aerobic respiration. But we also have something called anaerobic respiration, and it's similar to aerobic respiration, where we're going to convert organic molecules into something to make ATP, but it doesn't use oxygen. Okay? Fermentation is an example of anaerobic respiration. Okay? So cellular respiration is a slide I showed before. Okay? It includes both aerobic and anaerobic respiration, but it's kind of accepted universally that we'll be referring to aerobic respiration only when we talk about cellular respiration. Okay? So we got to do this reaction again. We're going to take glucose, which is this molecule here. When we add it with oxygen, you're going to produce a ton of energy. Water will be released and carbon dioxide. Okay? Plants will take the carbon dioxide, the water, and the energy from the sun and go this way to do photosynthesis. All right? Does that make sense? Now, let's do cellular respiration. Okay. So, we start off with glucose. Now, I do want to make point over here that this is inside the cell. This is going to be cytoplasm. This will be the mitochondria. There's things that will happen in here. There's obviously other organelles. This is the main one we're going to be dealing with. Glucose is a 6-carbon chain. Well, it's a ring, but let's make it a chain molecule. Okay? This is going to go through a number of steps, and this is just too big to get into the mitochondria. So we have to make them smaller. So we're going to make something called pyruvate or pyruvic acid. For your purposes, they mean the same thing. It really has one hydrogen off, but just, if you see the word on your test, or in your homework, or in your, or whatever you see in here, the book, pyruvic acid, pyruvate, meaning the same thing, okay? So we have pyruvic acid. Now, going from a glucose to pyruvic acid, what that is, it's a 3-carbon structure. So this is 6 carbons, and this is 3 carbons. But we have 2 of them. Does that make sense? Right? Easy math. Now, in the process of doing this, there's about 10 different steps, which I'm saying don't worry about. You want to learn those, go to biochemistry. Okay? I'm watering this down. But what happens over here is that we need to put in 2 ATPs to do this. We have to invest money to do this. What do you get out of it? You get 4 ATPs. So net-wise, doing this process, you do get 2. Hey, could I borrow $2? And then you sell something for $4, you have to give back the $2, or you had to invest that, right? So you make net 2 ATPs in this process. This process is referred to as glycolysis. And this uses no oxygen, so this is going to be anaerobic. Good so far? Let me know if you have any questions. All right, raise your hand. Now, what I'm going to do is to make this simpler for you to understand, I'm just going to be talking about 1 molecule of pyruvic acid coming in here. But know that when we deal with 1 glucose, 2 are coming in there. Right? Okay? I don't want, it's easier to follow that, because after you do all the calculations to figure out ATPs, then just multiply it by 2. Clear? Okay? All right. Now, if there's oxygen, this can enter the mitochondria. If there's no oxygen, then the only oxygen that the only ATP you can make is whatever's in the cytoplasm. But if you have oxygen, mitochondria is going to make you a lot of ATP. What happens to this pyruvic acid, if it can't get in there, we don't build this up. I mean, it does build up, but it goes through a different process, fermentation, that we can make, not AD, well, we'll get into it, but it does get reverted back to glucose. And we'll talk about that on Monday. But let's talk about if there's oxygen that comes, that is here. If there is, then we're going to have to process or prepare that pyruvic acid. So it's going to enter the mitochondria. When it enters the mitochondria, a few things are going to happen here. Because oxygen is there, O2 comes in, adds to this reaction, it's going to break off one of those carbons. And it gets attached to that oxygen. What do you, if you have 1 carbon and these 2 oxygens, what do you get? CO2, which is Carbon dioxide, right. That's one of the ways you're blowing off CO2. It's a byproduct. Make sense? This is now a 2-carbon structure. And now it has a new name. There's something that gets added to it. Okay? An acetyl group that gets added to it. And now this is called acetyl-CoA. And I'll leave all this up here if you want to take pictures of it. Acetyl-CoA is a 2-carbon structure. Okay? Again, from one glucose you get 2 acetyl-CoA, right? Okay? Now, something else that happens over here is that we're going to make some of this NAD or NADH. So what happens here is that we will have, we'll have NAD plus gets converted to NADH. All right? It gets reduced because the positive charge goes down, right? Same thing over here, which I didn't show you, but we also do the same thing. NAD plus, okay? And actually it makes 2. Or uses 2 to NADH over here. This is reduced. Questions so far? We're going to use this NAD later on to make ATP. So you're building up all this. This is like you're in America, but you got pounds and you got lira money. We got to convert it into something in a little bit so that we can use it as ATP. So the mitochondria only works if there's oxygen around. Now we could use this. And we have this Ferris wheel that happens in here. It has a few names. It's called a Krebs cycle or a citric acid cycle. And I like to just refer to it as the TCA, the citric acid cycle. This acetyl-CoA is going to enter this. And it's a cycle of a number of reactions, which again, you don't have to worry about. Let alone the structure changes in so many different ways. And there's an enzyme for each one. So you have a 2-carbon structure here, but we need to make things. We got to create something back to a 6-carbon structure. And we have something called oxaloacetate. Which is a 4-carbon structure. And that gets added into this. This whole cycle goes on, and for every one acetyl-CoA that comes in here, for every one oxaloacetate that comes in here, this will produce a few different things. It's going to produce two carbon dioxides. It's going to reduce more ADH. In fact, 3 NADHs and 3 It's also going to produce something called GTP. For our purposes, just know GTP as ATP. I'm going to make it simpler for you. And the other thing it does with FAD, it reduces to an FADH in one of those. The thing I want you to know about all these processes, not so much about the intricate steps as I'm kind of watering down for you. I'm more concerned about, for you guys, what goes into each process, what comes out of each process, where did it occur, how much ATP can you make? You need oxygen. But you don't have to worry about all those little steps and enzymes and all that stuff. Now look at this. The purpose of this Krebs cycle, the citric acid cycle, look at all the possibilities of ATP you can make. For every 1 GTP, you do get 1 ATP. For every 1 ATP, you get 1 ATP. That's obvious. Well, we have to invest over here. But here's where the big deal, the negotiation, not negotiations, but the best deal that you get in a store. For every NADH you make here, you get 3 ATPs. For every FADH you make over here, 2, you get 2 ATPs. We have to convert it. So we want that TCA, that cycle to work, because you get a whopping amount of ATP. But you need oxygen, because that oxygen has to come into, or allow the fibrilic acid to come into the mitochondria. pH, the GTP, the NADH here, the NADH here, the two NADHs over here. This can come in. Well, technically this GTP doesn't really go in there. It's already ATP. All of them need to be converted. So we have something called, as I mentioned to you yesterday, the electron transport chain. These are now carrying, because when reduced, this is now carrying electrons. This is now carrying electrons. So we got to change those electrons to power something to make ATP. Something to go from ADP and put that inorganic phosphate onto the ADP to make ATP. And what's going to power that is going to be these electrons. It's a pump. This enzyme, something called ATP synthase, is a pump to pump in these electrons, these hydrogen ions, which are the electrons, to crank this machine to, so to say, glue the inorganic phosphate onto the ADP to make ATP. The more electrons that are used, the more power play that pump has to make more ATP. This thing is called the electron transport chain. And it's not just one powerful thing, one big reaction. It's like I told you before, you can jump from the top of the stairs and jump right down, and that's explosive, but it's not controlled. You're not going to ask a woman who's like 90 years old who's got arthritis to jump that. It's not controlled. They're going to go one step at a time, so we don't lose any electrons. So there's a series of steps there. Whereby those electrons will power this thing. You're going to basically take ADP plus an inorganic phosphate. I'm sorry I'm making it so small, but you guys can take pictures of this, and I'll take pictures. It's going to go through here and make ATP. The electron goes further and further. Remember, just use the power. We're not going to lose those electrons. It's just used to power this thing. Okay? So what happens to the hydrogens that happen at the end here? Well, we got to have something that's going to accept those electrons and then move it out. The electron acceptor that's going to be over here is oxygen. The other reason why we need to have oxygen when we breathe. The oxygen is going to accept those hydrogens, and one oxygen accepting two hydrogens is going to make what? Come on. Basic. One oxygen and two hydrogens. Water, right. Okay? So what's going to happen here is as O2 gets over here at the very end, it's going to make water. That's the overview of this thing. There's three processes going on here. Glycolysis, this in parentheses, the preparation for the next step, but you have glycolysis, Krebs cycle, or the citric acid cycle, and electron chain transport. Questions about the big picture? I've simplified it. Believe me, I've simplified it. Carbon dioxide is wasted. We don't need that. We blow that off. We got it coming off there. We got it coming off there. But that's going to help the plants to, again, see how it all works. A big cycle.
That comes out through.
When you breathe. Mm-hmm.